Hello everyone, welcome to Math 115 College Algebra. So in this video I want to talk about rates of change and something called the average rate of change of a function, and we'll do that both, we'll do it actually graphically, we'll do it using a table, and we'll do it using an equation. And then I also want to talk a little bit about the behavior of graphs. So something called the local extremum, where is the graph increasing or decreasing, that sort of thing. Okay, so to start, let's see if we can find the average rate of change of a function. Actually, let me define it first. So basically the average rate of change, usually I'll just say A ROC or AV ROC for average rate of change, so I don't have to write average rate of change all the time. It's literally just the slope of the line segment that connects the two endpoints. So you can think of the average rate of change as being the change in output over the change in input, or the rise over the run, or delta y over delta x, or y2 minus y1 over x2 minus x1, right? All the definitions we use for the slope are the same for the average rate of change. Okay, so basically we're looking at how much one quantity changes with respect to another quantity. It could be like, if this is, let's say the average rate of change is a speed, so the change in output could be the number of miles you traveled, right? And the change in input could be the number of hours and time that you traveled. Or it could be like cost per year, right? So it's always going to be how one quantity changes with respect to another quantity. All right, let's look at this first example here. So this table gives the annual sales in millions of some product. And let's say we want to calculate the average change of sales between 1999 and 2000, between those 2 years. So the way I like to do this is let's write down the ordered pairs for the two endpoints, right? So we want to see what's going on during 1999. So I'm going to write 1999, comma, and what sales does it correspond to? It corresponds to 189 million. You can call it, let's say, since it's year, I'll call this like T1, and I'll call this like S1 for sales. And then we want to see how the sales change between 1999 and 2000. So the next point is going to be 2000. That would be like T2. And then the sales in the year 2000 were 210 million, right? So the S2. So to find the average rate of change, it's going to be the change in the output, which in this case is the change in sales, right? So it's S2 minus S1 over the change in the input, which is the change in time, T2 minus T1. So if I plug this in, I have 210 minus 189 over, and then 2000 minus 1999. So 210 minus 189 is 21. And then 2000 minus 199 is just 1. So this is equal to 21. And then what are the units? It's really, so remember the numerator is like millions of sales. Divided by, and the denominator is years, right? So it's like 21 million sales per year. Okay, using the same table, let's answer another question. What's the average rate of change between 1999 and 2004? Okay, so it's the same process, right? I will write down the information for 1999, so that will be the same as above. So this is 189. So this is T1, S1. And then for 2004, the corresponding sales is 234 million. So this is T2, S2. By the way, you can call these anything. I'm just using T because it's a year, time, and S for sales. But I think in my other notes I use x and y, right? So it doesn't matter what you label these. So you could use the traditional x and y if you want as well for your variables. Okay, so the average rate of change is going to be S2 minus S1, right? The change in sales, that's a change in the output, over the change in time, the change in input. So T2 minus T1. So in this case, it'll be 234 minus 189 divided by 2004 minus 199. In the numerator, I'm going to have, I guess, 45, right? 234 minus 189 is 45, divided by, in the denominator, I have 5, and then I can simplify that to 9. So the answer will be 9 million sales of that product per year. Yeah, I guess there should be no S up here, right? Just 9 million sales per year. So those are my average rate of change over those years. What if we ask for the average rate of change? Here, I won't do this out, but let me point to it. Let's say I want to know the average rate of change from 2002 to 2004. So in this case, right, it would be S2, 234, minus S1, 234, over T2, 2004, over T1, 2002. And notice that the numerator, 234 minus 234, is 0. The average rate of change over these 2 years happens to be 0, right? Million sales per year. So 0 sales per year in that case. So it really depends on the interval, the time interval that we're interested in. Okay, what about using a graph now to find the average rate of change on some interval? Okay, so in this case, I want to find the average rate of change from -2 to 3. So really what when we're given that interval there, I'm given the input values, right? This is kind of like my x1, this is my x2. So x1, x2. Right? That's the interval, those are the inputs. So what is the output? What is the function at -2? Well, it's going to be this point right here, right? So you could say f of -2 is equal to 1. And then what is the function at the right endpoint? That's this point right here. So basically f of 3 is equal to 3. So the average rate of change is equal to, I can write it as f3 minus f of -2, right? That's the change in the output over the change in the input, which is 3 minus a -2. Okay, another way to think about this, you can think of this is like y1, this is like y2, right? So this is also the same as y2 minus y1 over x2 minus x1, right? Same thing, it's literally just a slope. What we're calculating is the slope of this line that connects those 2 points, right? It's the slope of that red line there. Okay, so in this case, f of 3 is equal to 3, right? Or y2 is equal to 3. F of -2 or y1 is equal to 1. And then x2 was 3 minus -2. So this is just going to be 2 over 5, right? So that is the average rate of change. Okay, it's the slope of this red line. Okay, what if we have an actual equation for the function and we want to find the average rate of change? So in this case, I want to find the average rate of change, right, of this function x squared minus 1 over x on the interval 2, 4. So the 2 again is like the left endpoint of the input, and the 4 is the right endpoint of the input. So it's basically x1 and x2. And then the outputs are going to be f of x1 and f of x2. Right? So average rate of change. Here, I'll write it out again. It's y2 minus y1 over x2 minus x1. But that's the same. Y2 is the same as f of x2 minus f of x1 over x2 minus x1. So this is going to be f of 4 minus f of 2 over 4 minus 2. All right, what is f of 4? So f of 4, I go to my function where I have an x, I plug in a 4. So it'll be 4 squared minus 1 over 4. If you work that out, that's 16 minus 1/4. This is going to be, I'll just write it as a decimal, 15.75. Okay, and then what is f of 2? F of 2, I plug in a 2, so it's 2 squared minus 1/2. So that's 4 minus a half, which is 3.5, right? 3.5. So then I can solve this, right? This is going to be 15.75 minus 3.5 over 4 minus 2, right? Which is this 2. So this turns out to be 12.5 divided by 2. 12.25, sorry, divided by 2, which is 6.125. So that's the average rate of change of that function over that interval from 2 to 4. Okay, the next example is similar, right? So we're given an equation again. So I want to find the average rate of change. Well, it's going to be g of x2 minus g of x1 over x2 minus x1. Where again, x1 is the 1 here and x2 is the 9, right? Because we want over the interval 1 to 9. So first of all, let me find what g of x2 is g of 9. So what is that? Well, it's going to be 9 minus 2 times the square root of 9. So this is 9 minus 2 times 3. 9 minus 6, which is equal to 3. And then g of x1 is g of 1. So that's going to equal 1 minus 2 times the square root of 1. So that's 1 minus basically 2 times 1, which is 2, which is negative 1. Okay, so if I plug in now, this is going to be 3 minus a negative 1 divided by 9 minus 1. So this will be 4, right? 3 minus negative 1 is 3 plus 1, which is 4. And then 9 minus 1 is 8. And then I can simplify this to 1/2. So that would be my average rate of change over that interval. Okay, a few more of these. Okay, so find the average rate of change of the function from x equals 1 to x equals 4. Okay, so basically, again, at x equals 1, what is the point here? It's going to be 1, comma 1. So this is kind of like x1, y1. Or x1, f of x1, right? Same thing. And then at 4, what is the point? It looks like it's 4 is the input and 2 is the output. So this is like x2, y2. So now if I want to find the average rate of change, it's simply going to be y2 minus y1 over x2 minus x1. And again, you could have used the notation. Instead of y2, I could say this is f evaluated at x2, right? F of x2 minus f of x1 over x2 minus x1. So in this case, again, this y2 is the same as f of x2. And the y1 here is the same as f of x1. So this would be, I guess, f of x2 is 2 minus f of x1 is 1 over x2 is 4 minus x1 is 1. So it looks like it's going to be 1/3. And notice that is actually the slope of the line that connects those 2 points, right? Remember, the average rate of change is always going to be the slope of the line that connects those 2 points, the 2 endpoints. My rise is +1, my run is 3, so the slope is 1/3. So that all makes sense. Okay. The last question, so this is sort of a physics example here. You're told that this equation, x of t, so now the x is the output, the dependent variable, and t is the input. We do this a lot in physics, where like x would be like position and t would be time. So this gives the position as a function of time in this case. Okay, so x of t equals 2t squared minus 1 represents the position x in meters of a particle at time t seconds. What is the average velocity from 1 to 3 seconds? And my hint is the rate of change of position, right, with respect to time is defined to be the average velocity. So when I'm asking for the average velocity, I'm literally just asking for the average rate of change with respect to time. Okay, so average rate of change, right, of the position, it's implied with respect to time, is equal to the average velocity. And what is that equal to? Well, it's going to be the change in the output, change in x, over the change in the input, right? Change in time. So I could write this as it's x at t2 minus x at t1 divided by t2 minus t1. Okay, what is x at t2? Well, t2 was 3 seconds, right? I want to know the velocity from 1 to 3. So basically, like the t1 is the 1 and the t2 is the 3. So this is x of 3, which is going to be, if I plug it in, 2 times 3 squared minus 1. So this is 2 times 9 minus 1, so 18 minus 1, which is 17. And then x of t1 is x evaluated at time 1 second. So now I plug in a 1. And that's just going to be 2 times 1 minus 1, which is 2 minus 1, which is just 1. Okay, so if I plug in now, I have x of t2, which is 17, minus x of t1, which is 1, over t2 is 3, minus t1 is 1. So this is going to be 16 over 2, which is 8. But now it's not just a simple graph with no units. There's units here, right? It's a real problem. So what are the units? Well, remember the change in position was measured in meters, and then the time was measured in seconds. So it would be 8 meters per second. Okay, you can think of it as 8 meters per 1 second, but usually we just write 8, right, meters per second. Okay, so the average velocity is an example of, at least in one dimension here, is an example of an average rate of change, where the input is the time and the output is the change in position. Okay, next, let's talk just a little bit about where graphs, if we have a graph of a function where it's increasing, decreasing, and then a couple of special points on the graph as well. Okay, so this is a picture from the textbook. And the way you look at this, so if you want to figure out where a function is increasing by looking at its graph, you're always going to read like from left to right, right? You're going from a smaller x to a larger x. So if you start and this continues forward, right? If you start at, say, negative infinity, and you move to the right, you can see the graph is getting, the function, the output is getting larger and larger and larger and larger. So basically from negative infinity all the way to -2, the graph is increasing. Okay? It's also increasing from 2 all the way to positive infinity, because this, we're just assuming, keeps going forever and ever and ever. Okay, so it's increasing from negative infinity all the way to -2, and then from 2 all the way to positive infinity. And then it's decreasing here, right? So what interval is it decreasing? Like what's the domain basically where it's decreasing? It's decreasing from -2 to +2. Okay, so here, let me write that down here. So let's use black. So f is increasing on the interval negative infinity to -2. Now, when we talk about increasing or decreasing, we never include the endpoint, so I'm always going to use just parentheses. And then also, so I'm going to do union, and then 2 to infinity. And where is it decreasing? F is decreasing on, not including the endpoint, -2 to +2. Okay, so when you're talking about increasing or decreasing, don't include endpoints, because it doesn't make sense like right at an endpoint whether it's increasing or decreasing, because it could be what we're going to talk about in a second. It could be like a relative max or relative minimum. Okay, what's happening at these 2 points right here? So right at -2 and right at x equals +2. What's happening with the graph there? We'll notice, right, at -2, the graph is going from increasing to decreasing. So we have sort of like a little hill there. This is called a local maximum. So where you have like a little hill, there's a local maximum. So I'll write that here. This is a local maximum. Some people will say a relative maximum. So you could either use local maximum or a relative maximum. And in here, right, at +2, what's happening? Well, the graph is going from decreasing back to increasing. So right at that instant, right, where it's neither decreasing nor increasing, this is like the valley, you have a local minimum. All right, so here, I'm going to write that out in words down here. So at x equals -2, there is a local maximum. Right? Basically, there's like a little hill there, right? It's the top of the hill. And then in terms of, if they ask you for the local max is going to be the output value. So you could say the local maximum is and I have to go back to look at it. What's the output value? It looks like it's 16, right? So the local maximum is 16 at x equals minus 2. Okay, and then at x equals positive 2, there is a local minimum. Basically, it's where we have a valley. And then again, if I'm asked for the local minimum, that's really the output value. So I can say the local minimum is, well, what's the output value at 2? It looks like it's negative 16, right? So like the coordinates of that point would be 2 comma negative 16. The coordinates of this point would be negative 2 comma positive 16. So the local minimum, the local minimum is actually negative 16, and it occurs at x equals positive 2. So I can say the local minimum is negative 16 at x equals positive 2, right? That's where it occurs. And the local maximum and local minimum together are called relative extrema. So the local maximum and local minimum are called relative extrema. That's why sometimes people, instead of saying local maximum, local minimum, they might say relative maximum or relative minimum, right? It's acceptable. So when a question is looking, this should be extreme with an A there. When the question's asking for relative extrema, then you want to list whether there's a local maximum and or a local minimum. All right, there's also something called absolute extrema. Let me actually go back to the graph for a second. And I'll write it in here. So absolute extrema. The absolute max is basically the largest function value. Right, so the absolute maximum is the largest function value. But it has to be a real number, right? So infinity is not, because infinity is sort of like, is not a number, right? You're saying it grows without bound. So let me define these first, and then I'll explain what's going on with this particular function. So absolute maximum is the largest function value. The absolute minimum is the smallest function value. Okay, note, in this case, right, with this particular graph, because this graph goes to negative infinity and positive infinity, there is no absolute maximum or absolute minimum, right? So you could say there are no absolute extrema. right? And that's why the arrow's used here, right? It's saying it goes down to negative infinity and it goes to positive infinity. If it stopped somewhere, let's say it stopped right there at 20, then you would say 20 is an absolute maximum. Okay, but it doesn't. It goes on forever. We'll see examples in a second where there are absolute extrema. Okay, so actually let's look at 3 more examples now where we look at this. So here's example 8. Given the function p of t, right? So p is a function of time. Below, identify the intervals of increasing and decreasing, and then label the relative and absolute extrema. Okay, so first of all, where is the function decreasing? Well, it looks like it's decreasing. Make some room over here. It looks like it's decreasing from negative infinity, right? Because this goes on forever, like this, up. Oops. So this goes on forever like that. So it looks like it's decreasing from negative infinity all the way to 1. And then this little piece here, right? And then 3 to 4. So we can say it's decreasing from negative infinity to 1. Remember, we don't include the endpoints when we're talking about increasing or decreasing. And then union also from 3 to 4. And then where is it increasing? Well, it looks like it's going up here, right? From 1 to 3. And then from 4 all the way to positive infinity, right? It keeps going, going, going. So it's increasing um, 1 to 3, union, and then I guess 4 on to infinity. Okay, where are there... First of all, are there any local minimums or local maximums? Let's look for local minimums. So local minimums would be like little valleys, right? Yeah, absolutely, right? Here, so here is a local minimum. Here is a local minimum. Okay, so we can say there's a local min equal to, what's the output value at 1 here? So maybe negative 1. So it's negative 1 at x equals 1. There's also a local min equal to, I'm going to say maybe a, let's see, maybe a half. So it looks like that point is maybe a half. So let's say a half at x equals 4. And then are there any local maximums? Are there any hills? Yeah, right here at 3, right? And we'll say the output value, maybe not quite, but we'll say it's 1. So we'll say we have a local max equal to 1 at x equals 3. Okay, so this is a local minimum. This is a local minimum. This is a local max. Now, the question is, are there any absolute extrema? Are there any absolute maximums, absolute minimums? Definitely there's no absolute maximums, right? Because this function goes up to positive infinity, right? It doesn't stop at any finite number. So you could say there's no absolute maximum. But is there an absolute minimum? Yeah. This local minimum, right, at 1 here is also an absolute minimum because that's the smallest value of the entire function, right? The smallest value of the entire function is negative 1. So there is an absolute minimum equal to -1 at x equals 1. Okay. Let's look at another example. All right, what about this one? So this one we want to just find all the local extrema and then absolute extrema. So it looks like, well, are there any hills or valleys? Okay, so first of all, there's definitely a valley here. So that's a local minimum. And then there's 2 hills right here and here. So those are local maximums. So here's a local min. Here's the local max. And another local maximum here. Okay, so I'll say there's a local min, and it's equal to 0 at x equals 0, right? Because the point 0, 0 is where that valley is. Then there's a local max equal to 16 at x equals -2. And then there's another local max also equals 16 at x equals +2. Right, so there's 2 local maximums, right? They're both equal to 16, and one is at an input value of -2, the other one's at an x or input value of +2. All right, what about, so those are local min and local max. What about absolute minimums and absolute maximums? Well, because these are also the highest points of the function, right? 16 is the highest point. These 2 are also absolute maximums. Okay, so I'll say there's an absolute max equal to 16. Again, at x equals -2 and +2. And then are there any local minimums? Is there like a smallest value that the function takes on? Yeah, if you look at this down here, right? This is going to be the lowest point. So this is a absolute minimum. It's equal to like -10, I guess, at x equals 3. Right, so this point right here is an absolute minimum. All right, and the ones again up here are also absolute maximums here and this one here too. Right, because they happen to also be, they're both hills, so they're local maximums, and they also happen to be the highest value of the function, so they're also absolute maximums. Okay, and then here we'll do one more example. Go back to increasing and decreasing. So here's this function. Where is it increasing or decreasing? So again, I'm assuming it's going forever. I didn't draw this here, but assume it doesn't stop. Assume there's like an arrow going forever, and then this is going forever like this. So let's do decreasing first. Where is it decreasing? So it's decreasing from -infinity all the way to, I guess, -3, right? That's where it's decreasing. It's also decreasing from +3 to +infinity, right? Because this goes on forever. So it's decreasing from negative infinity to negative 3. Don't include the endpoint, right? Union, and then 3 to positive infinity. Where is it increasing? Well, it's increasing here, right? From negative 3 all the way up to x equals 1. So negative 3 to 1. And then where's the function constant? Well, in this case, it's constant over this time interval right here, right? From 1 to 3. Again, don't include the endpoints. Are there any relative maximums or minimums in this case? Certainly this is a relative minimum or a local minimum. And then this is a little confusing because different books give different answers, but some books will say that this, where it's constant, could be considered to be a local maximum. Others say no, it just has to be like a single point, like part just like the peak of a hill. And since it's constant there, it's not. So it depends on what book you read, but we won't trick you with that because it really depends on how you define it. Okay, great. Next time, we're going to talk about something called compositions of functions. So it's another way of combining functions together. It's like creating a function of a function where a function is the input to another function. So we'll get into that next time. Great, thanks.